Okay, hello everyone. Welcome you to the presentation of the paper ID 15707 96984. The title of this paper is the soft homotopy via Moore-Penrose inverse for the 7th International Conference on Smart and Sustainable Technologies 2022 in Split and Bowl in Croatia. The day of recording this video is on Tuesday 14 2338. My name is Bamrung Tausi School. I'm from Department of Electrical Engineering, Faculty of Engineering, Srinakarin Virod University in Thailand. Okay, the talk of this presentation of this paper will be we'll start with introduction, and after that we are going to talk about compressive sensing problem, and we will see the basic idea in decision criteria, which is the soft thresholding, and we will see the conventional method, which is the soft homotopy algorithm, and we will see the proposed idea. The first one, the first proposed idea is the soft homotopy, which is based on the conventional method, but we use it uses the Moore-Penrose inverse, and another one is the minimal version. Okay, is the reduced complexity version of this one. It's called soft minimal homotopy algorithm with Moore-Penrose inverse. Okay, after that we will see numerical example whether these two proposed methods will work well or not, and after that finally we will see the conclusion of this talk, this presentation. Okay, the basic problem in science and engineering would need to recover desired signal x of the length n is an integer, and we observe the data from the vector b is of the length m and n are integers. The length m and n can be also called output data, which should be which is the length of the real value output data and real value input data. The collection of data will be based on the transfer function matrix A or the modeling matrix A, and A can depend on each model, or it can be chosen up to the system designer. Okay, we have the input signal x, okay, which is unknown, and we would like to know here the vector x, and it is passed on to the system transfer function matrix A, and it could be added by it can be perturbed by the error or the noise due to the electric imperfection, and after that we get the observation. But in this work we will not consider the effect of the noise yet. If the noise is very low, we can approximate it as the product between matrix A, the transfer function, and the input signal x. Conventional method to recover the signal x, which might be sparse, means it means that some elements in this vector may contain several zeros. It is the method which is called linear least square, or someone may call simply least square. It is a very well known and classical method. It can be used for both noiseless case and noisy case. It is based on the L2 norm. Okay, and the explicit solution could be expressed depending on whether m is less than n, or the length of the input signal equal to the length of the output signal, or the length of the input signal is greater than the the output signal. Okay, in this case, we're going to consider the compression sink case or the underdetermined system, which is this one. M is less than N. And in this work, we propose two methods for spark signal recovery. The proposed methods make use of more Penrose inverse, and it is an iterative computational using computation algorithm using the soft thresholding criteria. Previous work include LS L1R, which is the least square criteria with L1 norm regularization. Another method related to this is L1 IRS. It is also a regulated criteria based on L1 norm. Okay, and but in this work we consider the soft thresholding decision. The soft thresholding decision would be based on the size of the value of x in minus a certain value of threshold, and the size is the size of that number. For example, -1 would give negative, and -1, and -7 would return -1 to us, or 0 if x is 0, and if x is 10, okay, we will get number 1. Yeah. Okay. The pseudo L0 norm needs to be introduced because it will be used as the way to count the number of non-zero elements in the vector x. Okay, and infinity norm will be the norm of maximum value of the absolute value of elements in the x. Okay, the soft homotopy algorithm is the method that used soft thresholding as described before, and it is the result of x plus the gradient of the least square criterion, and then this is the soft thresholding, and the criteria would make a decision based on the soft thresholding, the threshold value here, the lambda, and gamma will be the scaling factor, the shrinking factor, and we start from 0 as the initialization value. We have the soft thresholding value lambda 0 from this computation from the infinity norm, and our method will be the same as soft homotopy algorithm in reference 17, but we use the more Penrose inverse at this location instead of the typical A transpose. So we have additional A times A transpose inverse here, and the stopping criteria will be the same as this one, less than or equal to 2k. K is the number of non-zero elements in vector x. Okay, but another one will be exactly the same as algorithm 2. In algorithm 3, we use only k without 2k, and then we will see the simulation result here. You can see that our method, the red one and the blue one, can provide lower root mean squared relative error, and here with respect to the number of non-zero elements. So if we have more data which are not zeros, we are gonna have a little bit more error like this, and we compare it to the original soft homotopy algorithm. Here, the blue one, we get lower error, and this is the typical least square criteria, and here is the L1 regularization method, like LS L1R, L1 IRS, in reference 14 and reference 15. Both of these are convex, and it can be computed by convex CVX pies, which is available software. And here we plot it with k, but we change the gamma, the shrinking value, from 0.05 to 0.5. We can see that the error method are still lower than that. And here you can see the the result, once we use gamma equal to 0.95, we still get lower error. And here the result from very tiny value shrinking parameter, which is 10 raised to 20, and for the regularization parameter. Okay, in this work we propose two methods that use Moore-Penrose inverse. The additional complexity would require only the inverse of these two metrics, and the